limit as x approaches 0 of 1 plus ln, sorry, x times ln of 1 plus b squared, all raised to the 1 over x power equals 2b sine squared theta, where b is positive and theta is between negative pi and pi. So our goal here is to solve for theta. Okay. First thing we're going to do is we're going to do e to the limit as x approaches 0 of ln of 1 plus x times natural log 1 plus b squared raised to the 1 over x power. The exponent is going to come out in front of the natural log. And then I have ln of 1 plus x times ln of 1 plus b squared. And if I were to plug in x equals 0, I would get 0 over 0, right? This thing would be 0. And then this x is also 0. Okay. So I would have to use L'Hopital's rule. So the derivative of the bottom, we can start with that one. That one's just 0. Or sorry, it's 1. So we can ignore the derivative of x. So let's just worry about the natural log. So the derivative of the natural log is 1 over the inside times the derivative of the inside. So the derivative of 1 plus x times ln of 1 plus b squared. The only variable here is the x. The ln of 1 plus b squared is a constant since b is greater than 0, so we said b is a constant. So the derivative of cx is just c, the constant, right? So in this case, it's going to be the ln of 1 plus b squared. Now if we were to plug in x equals 0, I would get e to the limit, if I plug in 0, the limit's gone, so I have ln of 1 plus b squared in the numerator, and then this thing goes away, right? Because x is 0, 0 times the natural log is just 0. So that's going to be over 1, which is really e to the ln of 1 plus b squared, which we know is 1 plus b squared. So the e and the natural log cancel each other out. So that is going to equal the 2b sine squared theta, right? So 2b sine squared theta. Okay. So let's do some work there. Okay, I'm going to divide everything by b. So I'm going to get 1 over b plus b is equal to 2 sine squared. And I'm allowed to divide by b because we said b is positive. It can never be 0. Okay, now let's think about this. So b is positive, and I should have said it's a positive, or I should have said it's a whole number. So b is a whole number, so it could be like 1, 2, 3, 4, etc. So let's look at first sine squared, or sine, right? Sine is between negative 1 and 1. Oops, that's positive 1, negative 1. So sine squared is between 0 and 1. Okay. So 2 sine squared is between 0 and 2. Okay. So we know that 2 sine squared, that's going to be less than or equal to 2. So let's keep that in mind. Okay. Now 1 over b plus b. What is 1 over b plus b? Can we find a bound for 1 over b plus b? This one you kind of have to think about it, right? So b is going to be 1, 2, etc. So those are the possible numbers for b. So let's look at the smallest one. If I have 1 over 1 plus 1, that's 2. Okay, let's look at 2. What if I plug in 2? 1 over 2 plus 2, that's 2.5. Okay, so 1 over b plus b is always going to be greater than b. And if you want to give, say, okay, yeah, put there. So if this is greater than b, the smallest we can make this be 1, right? The smallest b is 1, right? So this will be, in other words, 1 over b plus b is always going to be bigger than or equal to 2. So I found a lower bound for 1 over b plus b, and I found a upper bound for 2 sine squared. Okay, so where do these two intersect? Let's think about it. 1 over b plus b is basically anything bigger than or equal to 2, that value. 2 sine squared is everything to the left of 2. So the only place where these two are equal is at 2. Right? See, they're only equal at 2. So my goal here is to solve for theta. Okay. So 2 sine squared and 1 over b plus b are the same when they're equal to 2, right? So I'm going to set 2 sine squared equal to 2. And that makes sine squared equal to 1. So sine is plus or minus 1. We had the condition that theta was between negative pi and pi. Okay, so let's see. Sine is positive 1 and negative 1 at pi over 2 and 3 pi over 2. But 3 pi over 2 is not in the interval between negative pi and pi. So I'm going to subtract 2 pi from 3 pi over 2 and get negative pi over 2. So theta is either negative pi over 2 or pi over 2. And that's our final answer. All right, let's look at another limit. So I have limit as n approaches infinity of n plus 1 times n plus 2 times 3n over n to the 2n power, all raised to the 1 over n. So this looks a little goofy. What I'm going to do first is set this equal to y. Now I'm going to take the natural log of both sides. So when I take the natural log, I'm going to bring the natural log inside. So it's like the natural log of this whole thing. The n plus 1, n plus 2, all the way up to 3n. Over n to the 2n, and then raise that to the 1 over n power. The natural log is going to bring this exponent out in front. So we get ln of y, limit as n approaches infinity, 1 over n times the natural log of n plus 1 times n plus 2 all the way up to 3n times n to the 2n. Okay, so just to be clear, how many terms are here? Or how many, I guess, quantities am I multiplying? So the key to this one is I can rewrite 3n as n plus 2n. So I can think of it like counting like this. This is the first one, this is the second one, all the way up to the 2n. So there's going to be 2n of these guys. And notice there's a 2n in the exponent in the bottom. So I can break up n. So in other words, I can break up n to the 2n like this, where these guys are 2n. So there's 2n of those. Okay. So this is what I'm going to do. So I'm going to leave the n on the bottom here, and then I'm going to have ln. Okay, so it's going to be like n plus 1 over n, would be the first one, times n plus 2 over n, all the way up to 3n over n. Since there's 2n of these in the numerator, there's 2n in the denominator, that means they're each going to have 1 n. So it works out nicely like this. And now I can use a property. Well, I'm actually going to break this up. So I'm going to do n divided by n plus 1 over n. So just so we're clear, I'm going to treat this as n over n plus 1 over n, which is 1 plus 1 over n. So I have ln of y is equal to the limit as n approaches infinity. So ln of 1 plus 1 over n. And by the way, I should bring this exponent out in front. Or actually, oh no, that's not an exponent. Never mind. Okay, we're good. Okay, so times, times 1 plus 2 over n, all the way up to, well, in this case, it's just going to be 3. But I'll just leave it as 1 plus 2n over n, all over n. And this one, I'm going to take advantage of ln of x, y is equal to ln of x plus ln of y. So I'm going to rewrite this whole thing. Okay, and this is just going to be a giant sum. So I can, again, rewrite this. So I'm going to have the 1 over n, I'm going to bring outside. So I'm going to have the sum of ln of 1 plus x, or sorry, 1 plus I over x. And I'll explain this formula in a second. I over x times 1 over n. I can just pull it out in front from I equals 1 to 2n. Okay, and here's why. So my index here is I. So what's getting increased here? It's only the numerator up here, right? So that's why I'm going to put the I there. The function here that I'm looking at is ln of 1 plus x. But what I'm substituting in for x is basically delta x, which is I over n. And sorry, this should be n. Okay. So this thing is really the definition of the integral. And just to recall, that looks like, f of x plus delta xi times delta x. Here the delta x is the 1 over n. And of course you have the sum. But in this case, I pulled it out in front because it didn't depend on I. So this is integral of f of x, which in this case we said is ln of 1 plus x dx, and this is equal to ln of y. But the question is, what are the limits? Okay, so what are the bounds of this integral? Let's think about it, actually. We're going to look at this number. Where does it end up at? Well, it ends up at 2n over n, which is 2. It starts from 1 over n, goes to 2 over n, all the way up to 2. So 1 over n is very, very small. This is basically, it's really close to 0. So the intervals I'm looking for are between 0 and 2. Okay. So now I can integrate this. So this one actually, we can use integration by parts. We're going to let u equal ln of 1 plus x. So du would be 1 over 1 plus x dx. dv is just dx. So v is just going to be x. So I have ln of y equals, okay, then we're going to multiply these two. So it's x times ln of 1 plus x, and minus the integral of these two multiplied, so x over 1 plus x dx. And let's not forget the bounds. So I can rewrite x over 1 plus x as 1 plus x over 1 plus x minus 1 over 1 plus x. Because these guys would just end up canceling and just have x left. So that'd be 1 minus 1 over 1 plus x. So I can plug in 2 actually for x. That'd be 2 times ln of 3 minus, if I plug in 0, this will just cancel it all. So I'm not going to bother doing that. And now I can integrate from 0 to 2 of 1 minus 1 over 1 plus x. So that'll be 2 ln 3 minus quantity. So here, because I have a negative, I want to put a bracket so not to make a mistake. So that'll be x minus ln of 1 plus x from 0 to 2. That'd be 2 ln 3. Okay, then now it's going to be minus, I'm going to plug in 2. And then minus, if I plug in 0, that's just 0, so I'm not going to bother. Okay, and I have, let's see, 2 ln 3 minus negative ln 3. That gives me 3 copies of ln 3. And then minus 2. So that's all equal to ln of y. So in order to get y by itself, I have to do e to both sides. So y comes out. And then I can rewrite this as ln of 3 cubed. And then times e to the negative second. Okay, and these guys cancel. I'm left with 27 times e to the negative second power, which is 27 over e squared. And that's my final limit.